Okay, today we begin chapter 5, AC analysis. It's one of my favorite chapters, especially the math. Okay, so let's one note, and I've titled this chapter as sinusoidal analysis because we mostly deal with sinusoid. Also, it's the name of the chapter in the book that I use. So what we're going to learn is when we have a AC source that supplies AC voltage or current, we will see how that behavior affects, how the alternating behavior of the source affects the resistors, capacitors, and inductors. So resistors work pretty much the same as they do for DC. So resistors work the same way as they did for DC. However, inductors and capacitors are energy storage devices. So when the incoming source signal alternates between a positive and negative peak, what is happening is that the energy is being delivered to the inductor and capacitor, and then it comes back out into the circuit, right? So it goes positive peak, negative peak, positive peak, negative peak. So the energy goes into the inductor and capacitor and then flows back out. So it's a constant exchange of energy flowing in and out of these components. And that's the reason why we need to study this behavior separately. But the good news is that we can mathematically model the entire circuit, including the sources as well as the components. In using complex math, we model it in such terms that you're able to use all of the DC analysis techniques as before. Okay, so we'd still be able to use Ohm's law, KCL, KVL, node voltage, mesh current. Don't worry, we won't actually do node voltage and mesh current for AC analysis, but we'll actually do the simple Ohm's law, perhaps KCL and KVL also, as time permits. Okay, but more importantly, it's about learning how to do the mathematical models for the sources as well as the inductors and capacitors. Okay, because the techniques are exactly the same. So once you are comfortable with the mathematical modeling, the techniques are exactly the same. So we are not learning any new techniques here. Okay. All right. AC waveforms, just showing a representation of a sinusoidal waveform and some of the other common ones that we see in electrical engineering. AC, if you think back to the first day of class, I talked about DC versus AC, right? DC stands for direct current, AC stands for alternating. The word alternating comes from the fact that the value of that waveform, whether it's voltage or current, alternates between a positive and a negative number. Okay. The word waveforms, again, here is simply a graphical representation, but the word wave and the word function and signal, they're all used as synonyms of each other. So if I use the word waveform, or I use the word signal, or I use the word function, they all mean the exact same thing, and they could represent either voltage or current or power. More often than not, we are talking about voltages. Okay, so if I say AC signal had a voltage value of, let's say, 5 volts, or I could say AC signal had a value of 5 amps, they all mean exactly the same, right? Waveform, signal, function, all are talking about AC voltages and AC currents. Okay, so here we have a AC waveform that is in the shape of a sine wave. Mathematically, we can represent this signal, this wave, as either a sine or a cosine function. Okay, a sine or a cosine function. X-axis is always time. We're in the time domain representation. Y-axis notes the actual value of that quantity. So in this case, it is showing or representing the voltage, and so it's V of t. Okay, voltage as a function of time. It could just as easily represent voltage, current, or power. Okay, voltage, current, or power. And then here we have some of the other more common ones: triangular, ramp, square, rectangular. Square and rectangular are something that we use in digital circuits, where it's on for a certain period of time, then it goes off, then on and off, so on and so forth. And that's kind of like a digital representation of a AC signal. The mathematical representation of a sine wave. Oh, sine waves are the only ones that we will look at in this chapter. Okay. So a mathematical representation is given by this expression: V of t is Vm cos omega t plus or minus theta, where t is, of course, the variable, and the quantity is a function of that variable. In this case, it's voltage. And again, as I just mentioned a few seconds ago, it could just as easily be current or power. So this representation could be for voltage or current or power. Okay. We have three quantities in there: Vm, omega, and theta. The M stands for the magnitude of that waveform. It's basically describing the value of that quantity on the y-axis. If this is 0, describing the magnitude or the amplitude or the peak value of the waveform. So in some books and some authors would refer to Vm as Vp. If you took the lab EE251 and you did lab 5, on the oscilloscope you would have seen Vp. In the lab write-up, you would have seen Vp. That stands for peak or the magnitude. In this course here on the online homework, you will see Vm. It is one and the same thing. It's exactly the same thing. The P comes from peak, M comes from magnitude. They're both describing the same quantity, same value for that quantity. When it's describing I of t, you would have Im or Ip. Still the same thing. If you wish to describe the waveform from its maximum to its minimum value, you would use the term P dash P, peak to peak. Okay, peak to peak. So Vp dash P is 2 times Vp or 2 times Vm. Two times Vm. Okay. Yeah. Yes, I'm getting to it. Yep. Is this clear though? The peak and the magnitude. Okay, they are one and the same thing. Now the three quantities all have different units. The overarching unit for this quantity, of course, comes from the fact that it's describing a voltage, right? V of t. So when you write an expression for an AC signal, depending on what the signal is, whether it's voltage or current or power, the units remain the same: volts or amperes or watts. But the three quantities inside, which is the magnitude of the voltage, that is volts. Omega is the angular frequency or the angular velocity, and it's in radians per second. When we actually go to the frequency domain in the complex plane, it's radians per second. And then the phase of the waveform is in degrees. Okay, the phase, there's a reason why the phase is in degrees and not in radians. You could, of course, convert omega, which again, omega is 2 pi f. So you can convert the phase, describe it in radians, add it up. But there is a reason we keep it separate. We will use this because we would do a transform of this function and do a mathematical representation as a vector. And so we need that phase angle in degrees. That's the reason why we do it. All right, so radians per second and in degrees. Okay, so when we do a transform, phasor transform for this, for the sine wave, the phase angle is described in degrees. Now, this function is used for both sine and cosine waveforms. They are one and the same thing. The mathematical difference between them is that sine x is cos of x minus 90. There is a phase shift of 90 degrees. And we will look at what each one of these quantities mean in the next 3 slides. Okay. Omega, the angular frequency, mathematically can be described as 2 pi f, where f is the frequency in hertz. We can get it from the time domain by the reciprocal of the time period, 1 over t. Okay. All right, let's take a look at these 3 quantities individually. The magnitude or the amplitude of the peak describes the value of the quantity on the y-axis. So it's basically telling you how tall or short it is. If you look at this waveform right here, the waveform in red has a value of about 0.5, which comes from here. Second waveform is simply sine theta. It's not listed. It's basically 1. And the third one is 2. Again, note that these values are only describing one peak. If you want to fully describe the waveform, this would be minus 0.5. This is minus 1. And this is minus 2. Okay, so the peak value for, let's say, the blue waveform is 2 volts, but the peak to peak value is 4 volts. All right. Make sense? Your waveform goes from 0 to a positive value, comes back to 0, goes below 0 to a negative value, and then comes back up to 0. When it does that, when it cycles through both a positive and negative value and comes back up to 0, we call that as one full cycle. One full cycle. And the number of cycles it completes in 1 second is named as the frequency. It is called as the frequency and noted by the lowercase f. The unit is Hertz, not the car company. It's named after a German physicist. Hertz, spelled exactly the same. Short is HC. This is also T, uppercase T. So in this previous equation, where I said frequency is the inverse of time, basically it's the time period T, and the inverse of that one time period would be the frequency of that waveform, where T is in seconds and F is in hertz. Okay, so it's the inverse. All right. So general knowledge question, what is the frequency of the power outlet? 60 hertz, right? Mentioned that on the first day. So it goes through a positive and negative cycles 60 times in 1 second. That's what it means. The value of that waveform cycles through a positive and negative values 60 times in 1 second, which is very, very low frequency, extremely low frequencies. It's below the normal hearing range of most people. Okay. It's the loud thumping bass sounds you would hear from a subwoofer. Just to give you a general idea, frequency of our wireless bands, microwaves, cordless phones are 2.4 gigahertz. 2.4 gigahertz, right? 10⁹. Everyone remember unit prefix from chapter 1? So it goes through that many cycles in 1 second. Phase. Phase is simply the point in time where the waveform's value, y value, the value of the y-axis goes to 0, and the moment in time, and that moment in time where it crosses the x-axis. Okay, so the moment in time where the value of the waveform goes to 0. This is t on the x-axis, time on the x-axis, and the waveform, if you keep your eye on the one in black, crosses the x-axis, or the value of that waveform goes to 0 when x equals 0, right? So the phase for that waveform is 0. So theta is 0. If you look at the waveform in blue, the waveform in blue and the waveform in red are crossing the x-axis at different points in time. Okay. If we consider the y-axis as a reference point as 0, when time is equal to 0, these are all positive values on the right. So I could say that's the future. This is the past. +1, +2, +3, and so on and so forth. To the left of the axis is -1, -2, -3, and so on and so forth. So speaking in terms of time, anything on the right of y equals 0, or sorry, x equals 0 is the future. Anything on the left is the past. So the waveform in blue has arrived before the waveform in black and red. The waveform in blue crosses the x-axis, let's say at -1, right? That moment in time has already passed. It's already beyond x is equal to 0. And the moment in time in the red axis of the red waveform crosses, let's call that +1. It is yet to arrive at 0. And so the waveform in blue, we say, is ahead of the other two waveforms, or more technically, we would say it is leading. It's noted by a plus sign. The waveform in red is behind or lagging, noted by a minus sign for the phase angle. Okay, minus sign. Let's take a 10-second pause while you think over that. Let me know if you have any questions. Actually, it does not matter, but you're right. Shouldn't. I'll change it here. This makes it easier here. That's good. No one has actually noticed this, in the last few years. It's 0.5. All right, any questions regarding phase? Okay. What is the average value of the waveform? An AC waveform, positive and negative. Half of it is above, half of it is below. What is the average value? 0. Yet power and energy is being supplied and delivered, right? So when they first came out with means of generating, AC current and AC voltages, obviously they are, when it's supplied, light bulb turns on, energy is being supplied, it is being delivered to the load. But they needed a mathematical way to actually describe that quantity. They take the average, it's 0. So what they decided to do was, instead of taking the average of the waveform, they would first square the waveform, mathematically speaking, then take the average. And because we did a square at the beginning, we now take the square root at the end. And so they came up with a new term called root mean square, which literally is the root of the mean of the square of the waveform. Hence the term root mean square. Square root of the average of the square of the waveform. Mathematically, it's represented by this equation right here. You can see, first take the square of the waveform, then you sum it up, right? Multiple slices, and then you add up all the slices, basically integrating from 0 to t for one time period. Then average it out, 1 over t, and then finally you take the square root of the waveform. Make sense? Right? Hence the square root of the mean of the square of the waveform. And it works for both voltage and for current. VRMS, IRMS. If you plug in voltage or current as a sine or a cosine function and you solve it, there is a 4 or 5 step derivation. We end up with this relationship. The RMS value of the waveform is the magnitude of the waveform divided by root 2. So it's Vm over root 2, or if you wish, Vp over root 2, Ip over root 2. So this is true only for sinusoidal functions, meaning sine or cosine. Okay, you can directly find the RMS value by dividing the peak value or the magnitude with root 2. This is only true for sinusoidal waveforms, not for any other waveforms. Okay, and there is a derivation. If you're interested, I can show it to you. Just stop by my office and I can show it to you in the book. All right. One last thing is basically the power. Power is still the product of voltage and current. For a resistor, we can find it as V square over R or I square times R. So those equations still apply. So the average power in a resistor can still be described by the same equations, except it would be V RMS square and I RMS square. All right. Okay, we'll end class here today, and we'll pick up here again on Wednesday. Open up the homework. Based on the concepts we have covered, you should be able to answer the short answer questions and the multiple choice questions in the next homework assignment.